Let's define vector spaces and subspaces a bit more carefully now and formally. We're going to simplify our definition a little bit. We will kind of circle back to this in a couple of weeks, and at least in the textbook you will see a write-up of the proper definition of vector space. But for our purpose for now, let's just define vector space as a set of all possible vectors of a given number of components. That is a vector space. It's also called a linear vector space, linear space, etc. There are two conditions. It should satisfy the closure properties of vectors, both for scalar multiplication and vector addition. And of course, the vectors should have these two operations defined and specified. So Rn is a vector space if you think of it as the collection, a set of all possible vectors of n components and real components. And also, if you think of Rn as the coordinate space where you have points and curves and surfaces, etc., that coordinate space also is a vector space. Let's simplify it and let's just consider R2, the coordinate space of R2, that is the xy plane. You have the x-axis, y-axis. Any point on that plane has a coordinate, x equal to something, y equal to something. And you can think of that as a collection of all these pairs of points, and each pair is like a vector. So there's a one-to-one correspondence between the points in this plane and an abstract vector space where you have only the collection of vectors that have two components. So there's a one-to-one correspondence between the coordinate space of R2 and the vector space of R2. You can think of set of matrices like Rm by n also as a vector space, because if you add two matrices of the same size, you get another matrix of the same size. So it's closed under addition and scaling and linear combination. And it's so common that you might vectorize matrices such as images for face recognition, for instance, and they might turn out to be column vectors in your program, but even though they are actually matrices. So it's a one-to-one correspondence there too. Complex numbers are basically very similar to R2 as a vector space, because complex numbers have the real part and the imaginary part, but it is very similar to R2. Real functions, that is an interesting situation. If you take functions, let's say defined between 0 and 1, you can think of that as a vector, because if you take one function and add a different function, you get a third function defined between 0 and 1. If you scale one function, you get a different function. So this is actually a vector, and this is the way of using vector spaces in situations where it may not be completely obvious, such as a Fourier transform, for instance. It's a way in which you can express a function of time by a bunch of functions defined within a certain time period, periodic functions really. And that comes about because you're thinking of the function that you want to express as a linear combination of the functions that you have on hand. Those are the basis vectors of the vector space that you're working with. A much more obvious way of using functions as a basis comes in quantum mechanics, in physics, where the wave functions are actually vectors in a complex space called the Hilbert space, and certain entities coming out of the wave function, such as its norm, turns out to be the probability of something happening in a certain space point or at a certain energy level, etc. And it has got the whole physics built on top of this idea of looking at functions as vectors. And with that simple extrapolation, the rest of whatever we learn here in our course can be applied and ported directly to quantum mechanics. The only thing that is special about the vectors there is the fact that a function defined as a vector between 2 points will have infinite points in the function. So a dot product between two vectors will not be a summation, it will be an integral. And also the vector space that you're talking about is not n dimensional, it's infinite dimensional. To make matters worse, Hilbert space is actually a complex vector space, but the rest of it is simple. Now that is vector space. It's closed under the two specified operations, and the two operations are of course defined. That's it. A vector subspace is a subset of a vector space. So given any vector space, let's say V, if you can find a subset such that it is closed under the same operations like scaling and addition. We actually dealt with it already. Can you see where? In example 2, we had a line in R2. So here I had two vectors, x1 and x2, but one of them was kind of useless because it was just a multiple of the other one. You just look at x1, take all scaled versions of it, all of them will fall in this green line. Take any two green vectors here, add them, it will still be on the green line because they are on top of each other. Scale any green vector, it will still be on that line. So this line of vectors is actually a vector subspace by our definition. It's a subset of R2, and any scale version of a vector on this subspace will be on that subspace. Any scale version, any scaling factor is okay. For that reason, if you scale this particular Z1 by 0, it should be in the subspace. That means all subspaces should contain the 0, 0. That is why we kept harping on the point that there's a line of vectors, the line going through the origin, etc. The second example was the xy plane. That was a subspace also. And remember, xy plane actually goes through the origin in R3. In other words, the 0 vector in R3, 0, 0, 0, is a part of the subspace. Then we had another example where we had a complicated pair of vectors, not the xy plane, some other plane, but that plane also contained the 0 vector. It has to be that way. If the subspace doesn't contain the 0 vector, it's not a subspace. Let me put it this way. If there is a subset of a vector space that doesn't contain the 0 vector, it cannot be a subspace by definition, because take any vector in that subspace, scale it by 0, and immediately you are outside the subset. So that subset cannot be a vector subspace. It has to be closed under scaling by any scalar. 0 is a pretty good scalar. Now, let's look at a couple of special situations. Remember, subspaces are sets, subsets really of vector spaces, which are also sets. All these sets contain infinite number of elements, but they are sets nonetheless. If you have two subspaces, S1 and S2 in Rn, let's say, the union is in general not a subspace. There are special cases where it is a subspace, but in general it's not a subspace. But the intersection is always a subspace. This is interesting. So let's take an example. So S1, the subset I'm going to define in R3, a set of all vectors with the first component anything, but the second and third component 0, is a collection of vectors that look like x0, 0. So that is basically vectors that lie along the x-axis. Now let's take S2 as a collection of vectors of the kind 0, y, z, y and z being anything. So that is basically all the vectors in the yz plane. What's the union of these two? You might be tempted to say that is any vector, but that's not true. You have to be careful here. Union means all the vectors that are along the x-axis plus all the vectors that are on the yz plane, but not vectors that are neither on the x-axis nor on the yz plane. And after all, those are most vectors in R3. So it's only a tiny subset of R3. So S1 union S2 is a set of vectors that lie along the x-axis or are on the yz plane. It's not a subspace because if you take two vectors, say 1, 0, 0 and 0, 1, 1, add them up, you get 1, 1, 1. Is it part of S1? No, because the second and third element, the second and third elements are not 0. Is it part of S2? No, because the first element is not 0. So it's not part of either. That means it cannot be part of the union either. So it's not in the union. So for that reason, in general, unions are not subspaces. Let's visualize example 1 so that we can understand this better. So here I have the 3D space rendered on my 2D screen here. I have x along the horizontal axis, y along the vertical axis, and z coming out of the screen toward me. So the first subspace we were considering is the red one along the x-axis, comprising vectors of the kind x0, 0. So they will all lie on the x-axis. Those are my red vectors, not just one, but many of them. Now, my yz plane, which was a second subspace we are considering, that is the green plane that is at an angle with respect to the screen, and the typical vector on that is a 0, y, z, the green vector. So obviously, any vector of the kind 0, y, z, by that I mean if you take any value for y or z, they will all lie on the green plane because the x value is actually 0, so it doesn't get out of that plane, it's on that plane. Fine, so that is a subspace, collection of all the vectors of that kind. Now the union of these two, union of my red subspace x0, 0, vectors of that kind, and the vectors of the kind 0, y, z would be just that. It's that green plane plus this just one line. to see the closure property, let's just add these two vectors. If you add x00 and 0yz, what do you get? You get xyz. Is that on the green plane? Unless x equal to 0, it's not going to be on the green plane. Is it on the x-axis? No, because y and z are some values, not necessarily 0. So it's like the blue vector that you see there, which is neither on the green plane nor on the x-axis. So the union of these two subspaces, being the green plane plus the x-axis, is not closed, because the blue vector literally is not on the green plane, neither is it on the x-axis. So that violates the closure property, and for that reason the union is not a subspace. But what's the intersection of these two things? Intersection in this case will be the case where x is 0 and y and z are 0 also. So it's just the 0 vector. It's just one element in a set, and that happens to be a subspace. Why? Because take any 0 vector in the subspace, scale it by any number you want, it'll still be 0. Take two vectors in the subspace, there's only one vector, so take it twice, add them up, you still get 0. So it is closed under scaling and addition, so it is a subspace. Now take another example. S1 is x00, so that is a x-axis, all vectors that lie on top of our x-axis. S2 is the xy plane. Now S1 union S2 is just S2 because x-axis is actually inside the xy plane, so it is a subspace. So this is a special case. S1 intersection S2 also is a subspace because that is the x-axis, which is a line going through the origin, which is a subspace. You can easily prove that it is a subspace also. Let's take the second example and try to visualize it. My first subspace was again vectors of the kind x00, collection of all such vectors that would be along the x-axis, either positive or negative. And that indeed is a subspace, is a line of vectors going through the origin. The second subspace was the purple vectors, xy0, collection of all of them. I have highlighted only the positive side, the positive quadrant, so that it doesn't clutter the picture too much. Now the intersection of these two things, the red vector being a part of the purple plane, the intersection is going to be just the red vector. That indeed is a subspace. But what about the union? Now you can see that the red vector is entirely inside the purple plane, so the union is going to be the purple plane, S2. So that also is a subspace because the purple plane to begin with was a subspace. It was a plane of vectors going through the origin, a plane going through the origin. It's a vector subspace. So there's a special case where unions can be subspaces. The smallest intersection is just a 0 vector, and that is a subspace. So intersection of two subspaces will contain at least the 0 vector, because all subspaces contain the 0 vector. It might be more than that, as you saw in example number 2, but it will have at least a 0 vector, which is already a subspace. That is the smallest subspace, a set containing just a 0 vector. But the unions are in general not subspaces, unless you have special cases like in example 2. So let's actually look at it a bit more. When are unions subspaces? In general, it's not a subspace, but when one subspace is part of the other subspace, like the x-axis and the xy plane, then the union is the larger of the two, which is already a subspace because both of them are subspaces to begin with. Union is one of them, so it's a subspace. If S2 is a subset of S1, it is contained in S1, then the union will be S1 because that is the bigger one, so which is already a subspace. Just to remind you and to reiterate, a set that contains just the 0 vector is a subspace, and it is contained in all subspaces. Therefore, if S1 is the 0 vector, S1 union S2 will always be S2, regardless of what S2 is, because S1 is just a 0 vector, which is already there in S2, and it is a subspace. So 0 vector union anything is always a subspace. So to put that down in black and white, if one vector subspace is fully contained in another, then the union is a vector subspace there. So that is all about vector spaces and subspaces. The next thing to do is to think about bases and dimensions of vector spaces and subspaces. That will be the next video.